Hello, welcome to the talk about the end of a myth. So I'm going to talk about a myth that has been believed for many years, many decades in database management. That is the fact that transactional management, operational databases couldn't scale. So a little bit about me. I've been a researcher and a professor for over 25 years. I devoted my whole scientific career to solve the problem I will be talking about. And just to tell you a little bit more about me, this has created a lot of fascination in Silicon Valley. I've been going to Silicon Valley periodically in the last 2 years, and I've been invited in the headquarters of the big tech companies to present what we are doing. I was 1.5 months ago at Facebook presenting this to the infrastructure guys there at Facebook, and I was last year at Twitter, Salesforce, and other big tech companies. So, a little bit about Lean-Scale. We are a new database vendor. We are doing an ultra-scalable operational database. I will go into details how we do that in the rest of the talk. We also do a database that is not only operational, but also analytical, in the sense that we blend the two capabilities of operational databases and data warehouses. And we have also an amazing storage engine that provides us with relational key-value data store with many nice features, in particular to bear the two kinds of workloads, operational and analytical, in an efficient way. So now let's go. Let's do a deep dive into the technical details. So, what is the myth? The myth is that operational databases cannot scale because transactions don't scale. The asset properties don't scale. Why people have believed this myth? The reason is that for over 3 decades it has been a fact that operational databases don't scale. So people just tended to believe that they couldn't scale because they haven't scaled for decades. Then there is also the issue that there are all the NoSQL vendors that, as you know, they provide scalable data managers, but they don't provide the asset properties, they don't provide transactions, and they needed a justification. So they used the cap theorem to tell why they didn't provide transactions. But as we will see next, it has nothing to do. So the cap theorem, what it states, is something very well known in distributed system theory. That what it states is that if you want to, you have replicated data, and not distributed data, replicated data, and you want to bear partitions in the network, you have to choose. You have 2 pieces of the system now partitioned. You have to decide whether you allow only a primary component to become available and provide services, or you want to have all of them providing service. If you have only one, you can guarantee the consistency because it's not talking with any of the others. But if you allow all of the partitions to work in parallel, obviously you lose the consistency across the replicated data. And you might see the cap theorem is talking about consistency, availability, and partitions. It doesn't mention scalability. It doesn't mention transactions. It has nothing to do with that. It's only to say when you replicate data and you want to tolerate partitions, you have to choose whether to provide consistency or to provide availability at all partitions at the cost of consistency. Okay. So now what we will devote the rest of the time is to the end of this myth. So what we have achieved is a distributed algorithm to process transactions for the operational database that is ultra-scalable. When I mention ultra-scalable is that we can scale out to hundreds of millions of update transactions per second, the transaction manager itself, I mean, and thousands of nodes. So basically, we have removed the bottleneck from where it was traditionally that it was in the transaction manager. And this has been also the result of devoting my whole scientific career to solve the problem and be lucky to find the perfect solution to it. So this is a micro benchmark that we did to see how much the transaction manager could do. So we were doing just sending transactions to a transaction manager deployed on 16 machines, and then see how much it was able to do. With 16 machines, the transaction manager was able to handle almost 2.5 million a-day transactions per second. Oh, okay. It's not going in sync. So let's go now into details how we have managed to scale transactional processing. So let's first look at how traditional systems process transactions and why they create a bottleneck. The thing is that for providing transactional semantics, you need at some point to serialize transactions. A serialized transaction means that they will appear one after the other, as they were not concurrent at all. Okay? So the way they have been achieved has been always to do some part of the transactional processing, typically the commit processing, in a sequential way. So committing transaction one by one. And that is what creates the bottleneck. It's like in a bottle. You have the bottleneck, and then all the drops go one after the other, and that is why the bottle cannot pour a lot of water. Okay? What we have done is very similar to what happens in the Iguazu Falls. In the Iguazu Falls, it's a huge river that goes to a cliff that is over 3 kilometers wide. And all the drops are going down through the fall without talking to each other, without synchronizing, without putting in a queue. That is what traditional systems do. That is why we can process massively so many transactions in parallel. Now the question is how we handle the transactional consistency. So the idea is that basically we allow transactions to do all of the commit processing but one piece fully in parallel without coordination. Okay? With this, what we allow is that any amount of work can be done in parallel and can be distributed as much as we need. Okay? But now, the thing is how you provide transactional consistency. What we do is that we regulate the visibility of this almost committed state. And we only make this state visible to the applications at the moment when we know that it's fully transactional consistent. Basically, there is a prefix, and there are no gaps in the serialization order. Okay? And with this, now let us go on how we do the parallelization of the different functions to parallelize the ACID properties. So a regular transaction manager has a structure like this one. So it's just a box. When I mean a box, it means a single computer that will be doing the transaction management. And then it takes care of providing all the ACID properties. Because it's a single computer, that creates the bottleneck. Why is a single computer? Because it has to serialize transactions and process commit one by one. That is why it's a single box. What we have done is to look in detail into the ACID properties, the ones that has to be provided by the transaction manager, and then we have parallelized each processing in a distributed fashion, every single ACID property independently, but in a composable way. Okay? So now, what we have done with atomicity. Atomicity is the all or nothing feature. If you are doing a wire transfer from an origin account to a destination account, you don't want it that if there is a failure, that the money has been withdrawn from the origin account and has not been deposited in the destination account, because customer of the bank will get really angry if this happens. So then we have the isolation of the writes. The isolation of the writes, basically, it's detecting conflicts, write conflicts. So this task can be parallelized very easily, because basically we have conflict managers that they are handling different set of keys, different set of rows, and then they detect whether two transactions that are concurrent, they are updating the same key. Then for the isolation of reads, we will look into detail, because that is where our magic happens. And then for durability, basically you have to make durable the updates of the transaction before notifying the client application. And for this, the way to scale this is to use as many loggers as needed. The key is that we can have as many loggers as we want because we don't need to be then in any particular order. While regular transaction managers, they require the transaction commit order is the same that happens on a single log. Okay. So our main principles for processing the transactions basically is that we deal with the conflict management before the transaction commit. So when the transaction is going to commit, we know it's already conflict-free. If it wasn't conflict-free, we have been rolled back the transaction before entering the commit. And then basically that we regulate the visibility of the committed state to guarantee the transactional consistency. So now, how is the cycle for the life cycle of a transaction? A transaction, when it starts, it gets assigned the current snapshot. The current snapshot is the view that you will get on the database. So to provide transactional semantics, you have to see as the transaction was a single point in time. There was no concurrent transaction, despite there are other transactions running in parallel with it. So you will have a view provided by the snapshot server that is telling you this is the current snapshot. This is the most recent view of the data that is fully consistent. And that will be the data that will be observed by the transaction. Then during the execution of the transaction, whenever we update a row, we will notify about the key to the relevant conflict manager. Conflict manager is handling a set of keys. And then if two transactions are modifying the same key, we'll go to the same conflict manager, and this conflict manager will detect the conflict between the two concurrent transactions. And then one of the transactions will be rolled back. And then the next point is the commit processing. That is a complex step that I will go into detail. So the first is kind of workflow, in which in the first stage, what we do is to obtain the serialization of that transaction. This is provided by the commit sequencer, so it's providing a counter. And then this counter is incremented. And basically, with this, that is the serialization of the transaction of the commit timestamp. With this, we make durable the updates of the transaction. We will go to a logger and store all the updates of this transaction labeled with the commit timestamp. And then at this point, once this is durable, then is the point of no return for the transaction. We can only go forward. And then at this point, the private updates of the transaction that were still not make the publicly available, then they are propagated to the storage layer. With this commit timestamp that provides a with a snapshot, they will be visible at some point. But at this point, we say they are readable because they are still invisible. Okay, nobody will still be able to view these updates till the snapshot server advances the snapshot to that point. And now we will see in detail that process. So imagine that we are committing 5 transactions fully in parallel, and they get different commit timestamps from 11 to 15. Now the current snapshot is at 10. So it means that any transaction that starts now will see any update with 10 or less as a commit timestamp. So now we are lucky, and transaction with commit timestamp 11 becomes durable and readable, and notifies the snapshot server. I'm ready. Because there are no gaps between 10, that is the current snapshot, and 11, we will advance the snapshot to 11. So now if we start a new transaction, it will observe this update, okay? Because it's 11 or lower, so it will observe this update. Now we are lucky, and then a transaction with commit timestamp 15 becomes durable and readable. This transaction, if now we start a new transaction, it will be still invisible. Why? Because there is a gap between 15 and 11. If we allow to read this, we may read things that are in the other transactions not yet visible, that might be part of what you're reading. So you will be observing an inconsistent state. What you have to observe is the snapshot at the timestamp, at the current snapshot, or the start timestamp where you started, okay? So now the one with 12 becomes readable and durable, At this point, we can advance the current snapshot to 12 because there are no gaps anymore. So if we start a new transaction, it will get us a snapshot, start timestamp 12, and then it will be able to view all the updates till that point. But it will not be able to serve 15 because it will provide inconsistencies. And then we have 14. In that case, we cannot advance the current snapshot. Then we will get 13, and now we can advance all of the sudden from 12 to 15 because there are no gaps anymore. So this is the way where we manage to provide full transactional consistency, but then we are not creating any bottleneck anywhere because everything that is happening fully in parallel, fully distributed. So to make things more efficient, some of you might have thought, well, the commit sequencer and the snapshot server, they are not distributed components. They can become a bottleneck. They will become a bottleneck with 1 million update transactions per second. That is already quite a few. There will be very few organizations doing more than that. But we can reach even to 1 billion update transactions if needed. Basically, what we do batching at every single stage, every single part of the transaction management. And basically, with this, we make the transaction management ultra efficient because whenever we send a message, we don't send a message for the single update. We send a message for 1,000 updates. Instead of sending a single message per transaction, we are sending a message for 1,000 transactions. And therefore, we can amortize the cost of the fixed cost of sending a message across 1,000 transactions and making it very, very efficient, despite being a highly distributed architecture and algorithm. So the transaction processing has one key advantage, that is all what we do, all this magic that you have seen, is fully transparent to applications. You can use us as you use Oracle or DB2. It's transactions. You don't have to do sharding. You don't have to do anything. You don't have to care to know in advance which rows you are going to read or to write. Okay? It's fully transparent. You use us with the JDBC driver, and you use a standard SQL, a standard transaction bracketing to start a transaction, commit transaction, and that's all. So in terms of architecture, we have three main subsystems. We have a storage engine that is a distributed key, a relational key value store that we have developed with 8 disruptive innovations to be able to handle efficiently both OLTP and OLAP workloads. We have the distributed transaction manager I just presented, and we have then a distributed query engine that is able to distribute both OLTP workloads and OLAP workloads. So it's basically it's like a distributed data warehouse engine that is working directly on the operational data. That is why we can deliver analytics or operational data, real-time analytics. So let me go a little bit deeper on this capability. As you know, today, the world, you have an operational database on one side. That is where you keep the operational data, and it's fully consistent because of the properties of the operational database. But when you want to do analytics, analytical queries, you have to go to a data warehouse. Because there are two separated systems, now you have to copy the data from one into the other doing an ETL process. And this is very expensive. It has been estimated by several studies that goes between 75% to 80% of the budget of doing business analytics. So what we have done is to blend the two capabilities into a single system, and now we have a data warehouse engine that is working directly on the operational data. So what you serve is real-time analytical queries. So now let me, in the last part of the talk, mention some use cases we have identified working with several companies, big companies. The verticals that we have found are all that are data intensive, like banking and finance, telco, insurance, retail, transportation, e-commerce, and so on, and gaming platforms as well. And I will go through some of the use cases we have identified with them. So one of them is for bankings and all users of mainframes. As you know, mainframes are extremely expensive. And because it's the only infrastructure that is able to bear very high operational workloads. We are the only database in the world that can substitute the mainframe and can do on a standard hardware. We can do on a commodity cluster. We can do in the cloud. Also, because people are used to have the mainframe, a big box, we are partnering with Bull to be, they are building a huge machine that they make a press release just last week. It's a machine that in the maximum version we reach 896 cores and 140 terabytes of main memory. So we are creating an appliance with them, and this machine will be able to solve any workload, operational workload in the world. And we are able to provide replication across of these two machines after replication. So at some point, when people trust lean scale, they will start thinking about migrating from the mainframe into our database. This will not happen now, but it will happen in a couple of years. We already have the right partners to do so. So another use case that we have found is in telcos. The telcos are extremely data intensive, and they have to waste so much time doing engineering, not to break the database. They have to do sharding. They have to know where they have put the data. Then they cannot query the data across the different shards. So they are wasting like half of their engineering time to overcome problems that had to be solved by the database. In our case, is what we are doing. We are solving the problem for you, so you don't have to care anymore about the data. You know that the database will not break. It will scale as much as you need. It will bear any workload that you want to put into there. So what they have found that is very interesting from the business side is that today they have to have multiple systems. For instance, for the consumer experience management, that is very expensive because they have to put all the raw KPIs into the operational database. They have to do ETLs into another layer for creating analytics. So they're having, with one telco that we are working with, they're having 2 clusters of 50 machines each. With our technology, they can just simply have a single cluster. And with this, they are halving the cost, the operational cost. So the people that have to take the shifts overnight and so on is proportional to the number of machines. Now they have exactly half. So they are halving the operational cost by means of using our database. Another interesting part is that our database will be fully elastic. We're able to move regions of data from one server into another. So with this, then you can balance the load dynamically, and you can also elastically provision new nodes and decommission nodes. So for IoT applications, we have something that is also very interesting, because our storage engine is a relational key-value data store for tasks that are very data intensive, like data ingestion in IoT, large IoT applications like smart grid. Then you can use the key-value interface to ingest the data, to insert the data. To do an insert, you don't need SQL at all. You can use the key-value interface, and then you are saving all the cost of the SQL processing. But then the data is relational, so it's still visible to your SQL, so you can still query the data in the same way you would have done if you are inserting the data using SQL. But then you are saving a lot of resources for processing these kind of workloads. And in travel tech is a very interesting industry because they have a very low margin. They have between 4 and 5% of margin. So the cost of infrastructure is very important for them. And for them, the ability of having real-time analytics is also key, because they can provide, they can do intelligence about the prices of the competition and do much better offering. And they need to do it in real time. To learn what happened yesterday doesn't help very much to today, that might be changing in real time. But also the fact that our infrastructure is elastic allows them to adjust the resources to the load they are receiving. And with this, they are able to save a lot of money when they deploy in the cloud, and then because they pay per use. And then they have high season, low seasons, then they know that the database will adjust the resources to what exactly they need. And that's all. So I'm here to answer any question you might have. cannot see anything with
Hi.
the lights in my eyes. So
Congratulations on the product and the throughput, actually. And I was wondering if you have any comments on latency and whether the snapshot manager handling out-of-order commits affects peak latency. Thank you.
okay, so in terms of latency, what I can tell you, we have been running the industrial benchmarks. In particular, for the operational part, we have been running TPCC. That is the standard benchmark for operational databases. And there, we are getting an average latency of 30 milliseconds. If you look at the published results by all the competition, that are results just done by the benchmark, you will not be able to reproduce at home ever. They were getting something like 120 milliseconds. But in practice, if you deploy one of the leader operational databases, you will get typically a latency of around 150 to 100 milliseconds. We are getting 30 milliseconds. So it's almost an order of magnitude below. More questions? Comments? Okay, so thank you so much for attending the presentation. I hope you enjoy it.